Okay, so today we're going to introduce Gaussian, kind of talk through all of the different options. Um, there's way more to this program than we can cover. So what we're going to be doing is focusing on just using Gaussian for spectroscopy, because that's what the course is focused on. But it's probably just as useful, or maybe for some people's opinions, more useful for thermodynamics. So looking at bond energies and enthalpies of reaction and Gibbs energy of reaction and so on. So the skills that you learn in this course, at least for building molecules and so on, you may use in your research, but you may not do the spectroscopy part. You may be doing it for equilibrium constants or for Gibbs energy of reaction and those kinds of things. So moving forward, if you do need help, in your research using Gaussian, I'm available for answering questions. Even though it's not related to spectroscopy, I also teach thermodynamics, and so I can help you with the thermodynamics part of Gaussian too. So I got, as I talked about in the meeting with you guys about taking on students over the next year, I'm definitely willing to work with you as a committee member. Okay, so I can be on your committee. And I know it's a little early for the new students to be picking a committee, but once you pick an advisor and you start doing your research, be thinking about who your committee members are going to be, and don't just pick somebody because you think they're nice. Pick someone who might have a good contribution to your research, because they're going to be reading your work. They're going to be the reading of your work shouldn't just be copy editing, like, oh, you made a typo. It should be somebody who could contribute. And the earlier you get them involved and give them briefings on how your work is going and so on, the more input that you can get. So you have one main research advisor, but you can have a couple of other folks that you collaborate with and can incorporate some of their ideas along with your advisor's approval, of course. But it really makes for not just a strong thesis, but a better education. Like you get the more collaboration, the more you learn. And so you can get to benefit from multiple professors' work. So be thinking about that as something that you want to look into. So let's look at Gaussian. Our pathway into Gaussian is going to be GaussView. So really today we're talking about Gaussian, but we're showing all the pictures of GaussView because Gaussian is the engine behind it. You guys are blessed because when I was learning Gaussian on my own in grad school, I didn't have GaussView. There was no graphical interface at all. If you wanted to build your molecule, you had to get in by hand and type in the Cartesian coordinates, and that was disastrous for a diagonal bond. Right? Sine of R, cosine of, and all of that. And so instead of having to do that, Gaussian incorporated a thing called the Z matrix. And so the Z matrix is nice because it's all in internal coordinates, like the bond lengths and bond angles and dihedral angles and so on. So you could at least use the Z matrix to define your molecule. And it was much easier to build molecules that way. In some senses, that's a superior way because then you know how you've built the molecule for Gaussian. And like if you're looking at a rotation around a dihedral angle, you defined that angle. And so you know which variable you're interested in. And so when you look at the output, you can see, is that angle 60 degrees or 120 degrees or 180 degrees? If you're looking at, say, like the backbone dihedral angles in a protein or something like that. You could define those in the Z matrix. Whereas if you use GaussView, it's a little more tricky to define those. You still can, but it's not as easy. Or someone might say it is easier, but because I learned it the old way, I think some sort of hybrid approach between using GaussView and then getting in there and editing the Z matrix is the way to do it now. But that's just for building molecules. Right now, building the molecule is easy. You have this GaussView window that you see here, and you can. Oh, it's not up? Okay, thank you. Here we are. Coming up. 3, 2, 1. Try it again. Yay. Okay. So this, yes. So here we have GaussView, the window, and you have right here 3 little builder tool things. One is just the different atoms in the periodic table. One is rings, and one is like functional groups. And so this is just where you start. Whatever molecule is shown here in the middle of this parent window, you click here, that's what you're going to get. And then if you want to put another methyl group on here, you just click any one of these hydrogens and it's going to add it on. So, so it's very easy to build molecules. There's also a ring. Well, here's, if you were to click, so here it's just carbon tetrahedral by default, but if you click this right here, then you can change what you're building with. If you click that, you get this periodic table. And so you can click any atom in the periodic table. When you click an atom, you get its most common valences. You can put just a plain carbon atom on something, or you could do this sort of alkyne, this double bond on both ends, something that's fully saturated, maybe even aromatic. So you can build all kinds of molecules from scratch using the various atoms. Now, it's interesting, Gaussian won't tell you if it can't model that element, okay? So you might pick something, like one time I had a project that this guy wanted me to look at uranium oxide. So I was building uranium oxide and my calculations kept failing, and I would look at the output file for my failed calculation and it says uranium is not in this basis set, okay? Yeah, and so I had to then go to the manual and find out the basis sets that cover uranium. Because most basis sets will get you through krypton, okay? And so they'll do the first 4 rows, but then they only have parameters for up through krypton. And so if you're doing anything for, larger molecules, let's say you have you've got a model that uses nickel and now you want to do palladium, well, you may have to change your basis set and switch over to a basis set that covers the full periodic table. Okay. Now, what's interesting is this is allowing you to put the initial guess of how the molecule is bound together. But these, whether it's a double bond, a single bond, and so on, is what Gaussian's actually going to compute. So you're doing an initial guess of the structure. And then you give that geometry to Gaussian, and then it optimizes the geometry. And it will determine whether it's a fully like traditional double bond, or if it's for some reason elongated and has like a 1.5 bond order. Even though you're looking at this saying this shouldn't have a 1.5 bond order, Gaussian's just displaying it as a little bit longer than a double bond, okay? And it's calculating the electron cloud that's holding the nuclei together. If you were to click this little ring button here, then you get these different ring fragments. And so this is nice because it saves you a lot of headache trying to build a bigger structure. You can put on these different ring structures. There's also one for functional groups. Now, once we have the molecule built, then it's time to do a calculation. And so you click calculate and you click that first thing, Gaussian calculation setup. And there are other kinds of calculation engines that GaussView will work with, but we have Gaussian installed here. And so you click this top one, or you could use a hotkey, Control-G, and you'll get this dialog box down here. And most of today's lecture is going to be talking about this dialog box here that you get after you click calculate. Okay. And so here we have this dialog box, and we'll go through the various tabs. We'll talk about job type in a minute, so let's just start on the second tab, the method tab. So you can pick here the ground state, or you can pick excited states. Like if you're trying to do some reaction where the excited state's important, maybe you have a photochemical reaction and you've excited the molecule, what's the geometry of the excited state? And so you can solve for excited state geometries. Then you have the level of theory designation, and then you have the basis set designation. Now the level of theory, we'll talk about in a second, it's related to the Hamiltonian, and then the basis set is related to the wave function. So we had Schrodinger's equation, right? You had the Hamiltonian operating on the wave function. And in this case, the wave function is governed by those basis sets. And the Hamiltonian is the level of theory that you're using. So we're actually picking whatever computational model we want to handle the Hamiltonian and the wave function to get the energies. There's also the charge on the molecule, so you can do atoms, ions, you can do those. And then singlet or triplet. This is important. Depending on the ground state of the molecule or excited states of the molecule, you can model singlets and triplets. Most famously, oxygen, ground state oxygen is a triplet. So it's like a diradical. There's an unpaired electron on each oxygen as opposed to being in a like a double bond. You know, it's got a couple of unpaired electrons in an excited state or an antibonding orbital. And so this model chemistries, let's think about this. Whenever you started out in organic, you probably bought a model kit, right? And what if you bought a model kit from this particular vendor and you bought a model kit from a different vendor and you built methane, okay? Or let's do water, it's easier to picture. You've got the OH bond in water and you get your ruler out and you measure it and it's 2 centimeters, okay? And yours, you have a different model kit, it's a little bigger, you build water and you look at it and you measure and say, no, the bond length is 3 centimeters. Can you tell it would not make any sense for y'all to argue with each other over whether it's a 2 centimeter OH bond or a 3 centimeter OH bond? Why is that? It's because you're using different models. Same thing for computational chemistry. You can't give a result without also telling people the model kit you're using. So the model chemistry is this coupling of the Hamiltonian and the wave function. You have to specify which Hamiltonian you're using, which wave function you're using. And then you can talk about bond lengths, bond angles, energies, delta G, all of that stuff, okay? But it's dependent upon the model chemistry. And so you would never try to take an energy difference from one model and compare it to an energy of a different model because you're using a different model kit, or we call them model chemistries, okay? So we have in this model chemistry selection of a theoretical model. I've been calling that sort of the approximation to the Hamiltonian, and then a selection of a basis set. Now, sometimes the model chemistry has both of those built in, and you just select one item and it has both in it. But a lot of times you have separate model chemistry and a separate basis set. And then we're going to talk about graphical models. We might not get to the graphical stuff today, so we'll do that on Friday. That's why this one lecture is split over 2 days. So once we're finished with the calculation, we can use GaussView to explore more things about the molecules, like its molecular orbitals and its electron densities, how, you know, where are the electrons holding the molecule together? And then also where, if I were to walk along this electron cloud, would it be in general a positive part of the molecule or a negative part of the molecule? So that electron density is going to tell us something about the charge distribution around the molecule. And that's important for reactivity, right? If you have an anion and it's wanting to find like a positive area of the molecule, it's a nucleophile, it's going to find a positive part of that molecule. We can model where those positive places will be. I kind of wish that we had taught PChem between Gen Chem 1 and 2 and organic, because then you would know so much more about the electron cloud, about molecular orbitals, how charge and molecules are held together. And then if you knew a lot about computational chemistry, you could determine with Gaussian what a nucleophile is, what an electrophile is, where nucleophilic attack would happen, where electrophilic attack would happen. And that's probably, you know, as you get more advanced in organic, they start using computational chemistry more and more. But how fun would it be to have had spectroscopy and all of this molecular orbital stuff and symmetry and then go into organic? What I think would happen is it would actually make better organic chemists, because they would be getting it last when they really understood it, as opposed to first when they struggle with it, and then they get PChem. Yeah. So, but no one has ever really entertained my idea of letting me experiment on a whole class of students to go right into PChem 1, right out of Chem 2. You know. It'd be a little steep climb, but I think it would really be great in organic, because then they would get to organic and they're like, this is great. Yeah.
Pascal rate for organic?
It might, yeah. Well, first of all, it would definitely, because people would have to jump over a hurdle before they got it, another hurdle before they got into organic. Yeah, but the pass-fail rate at PChem would go sky high. Just based on study skills, it's the more mature student that finally hits me. But if I was getting sophomores, it might be a little different story. Yeah. And so let's talk about the one of the foundational assumptions that we have for being able to do these calculations, and why we call it electronic structure calculations. The nuclei essentially are fixed because they move so slowly. And so have you ever been in a cloud of gnats? The little gnats that fly around your face, and you move and you wave your hands and they're still there. Like you can't get away from them because you're so heavy, you're moving really slow. All right, and the gnats don't even really know you're moving. So no matter where you move, then they can keep up. And it's the same with the electrons. So this bond stretching of the hydrogens is moving, and the electrons can adjust instantaneously. And so whenever we want to calculate the structure of the molecule, we can separate their motions. So this is the approximation, the Born-Oppenheimer approximation, that allows us to separate the motion of the nuclei from the motion of the electrons. And so in Gaussian, we fix the nuclei coordinates, and we calculate the structure of the electron cloud. That's called electronic structure calculation. And then we can move the nuclei and calculate it again, and move the nuclei. And we can minimize the energy that way. Or if we just sort of get a couple of points with the nuclei positions, then we can take the second derivative of that electron cloud with respect to the nuclear positions, and we can get the vibrational frequencies. So we can kind of see what that potential well is for all of the motions of the molecule, still using the Born-Oppenheimer approximation. So this is a really important approximation that allows us to do these calculations. Now let's talk about the energy equation. Thanks. So the molecular Hamiltonian is what allows us to solve the Schrodinger equation given the molecular energies. And so this is what we have for our Hamiltonian, where T represents kinetic energy. So these two are kinetic. And the V's are potential energy. Okay? And we know what the kinetic energy of the operator was when we were doing the particle in a box. That was that minus h bar over 2m, in the second derivative operator. So this is our Hamiltonian for a molecule. It's huge, okay? And this isn't even the full equation. I mean, this is the Hamiltonian. It's still got to operate on the wave function. And all of these things have to go through the wave function. So we have something with 5 terms in it that has to operate on the wave function. And so then that wave function is going to essentially be multiplied by 5 because it's going to multiply through. And we're going to have the kinetic energy of the nuclei and the kinetic energy of the electrons, and the potential energy of the nuclei, and the potential energy of the electrons, and the potential energy of nuclei-electron attraction. And so let's just look at the signs first off. So we have the Hamiltonian, the kinetic energy operator comes in with a negative sign, okay? Essentially the more, and so then we have those. When we do the second derivatives, though, those signs go away. It's typically, we get positive real results. But let's look at this potential energy. This is nucleus versus nucleus. And so it's positive, okay? So as the charge on the nuclei go up, we have a more repulsive potential. It's a double sum. So these alphas, let me go through here and say the alphas and betas are the nuclei. The I's and J's are the electrons. So the I's on this particular equation here are not imaginary I, they're just an index. So we're keeping track of the electrons with I's and J's. The capital M is the mass of the isotope that we're dealing with. So it makes a difference whether we're doing carbon-12 or carbon-13, even though it really doesn't change the electrical charge, it changes the mass. And then ME is the electron mass. And then this del squared, this upside down delta, is the second derivative operator. So just like the Hamiltonian was the second derivative with respect to x, we have x, y, and z here over all space. Or if we're in a centrosymmetric system, we can have r theta phi. But it's basically all three coordinates, the derivative with respect to all of those. So we have a triple second derivative times our huge wave function, okay, with respect to the locations of the nuclei. And then the triple derivative with respect to the locations of the electrons. And those are the kinetic energies. And then we have the potential energies. We have the repulsion of the nuclei based upon the charge on alpha nucleus and charge on beta nucleus. And so we pick nucleus 1, alpha equals 1, and then beta is every number greater than 1. So we say, what's the potential of nucleus 1 to nucleus 2, 3, 4, 5, 6, all the way up to n. And then we go to alpha equals 2, and then we do 3, 4, 5, 6, 7, 8, 9, 10. So this is an enormous double sum on all the nuclei. And then for every nucleus, we do every electron. And you can think about, carbon comes in with 6 electrons. And so for carbon, then we do the attraction, and it's an attraction term. It's negative here. So we have nuclear attraction. We have the charge on the nucleus here. And then this is this is the number of protons. Let me go ahead and go Z here. Z is the number of protons in the nucleus, and then that little e is the elementary charge. And so one is positive, one is negative here, so we end up with the negative out front. And so this is the elementary charge squared. That's the positive protons and the negative electron. And this is multiplying by the number of protons. And so that's getting all of the charges correct. And then this electrical potential is the charges over the distance between the two charged species. So this is something you saw in your physics class, electricity and magnetism. And so we pick a nucleus alpha equals 1, and then we go to all the electrons in the whole molecule, not just the ones hooked to that nucleus. And then alpha equals 2, all the electrons. Alpha equals 3, and those are all the attractions of all the electrons to that particular nucleus. And this is why we have a computer do this. Right? And then here is the electron-electron repulsion. And this is where we have a problem. This is called the electron correlation term, and we're treating the electrons as waves. And so it's really hard to pick a location for the electron. We have an electron probability distribution, but this term really doesn't have an analytical result. So we were able to do the particle in a box and particle on a ring analytically. We just do the algebra and the calculus, and we get a non-zero real answer. And we're done. We solve for the energies. We can't do that for a molecule because of this electron correlation term. So it's unsolvable. Even for something as simple as like a helium atom. Because we have 2 electrons in helium. We can do He plus, and we can do uranium 91 plus. Okay, but we can't do anything with 2 electrons, even an atom with 2 electrons. We still don't know the solution to that. Okay. Now maybe there's going to be some new calculus method or whatever that allows us to solve that in some time in the future, but at this point we can only do approximations for this electron correlation term. And I think it's a real problem because we have to take into account the dance of the electrons. They're acting as waves in this really complicated system. And so how do those waves interact with each other? It's not as simple as particles when we get to the electrons, because the wave character on a nucleus or on a molecule is dominating. It's not a particle orbiting a nucleus. It's the wave oscillating around the nucleus. And if we just have one electron, we've got it. We can solve it. That's what gives us the s orbitals, the p orbitals, the d orbitals, the f orbitals. Those are the solutions to the one electron atomic orbital problem. Those are called hydrogenic orbitals for a reason. It's that this hydrogen solution. But we don't have a heliogenic solution. Right? And so because of that, all of those p orbitals and d orbitals and so on that you learn really only apply analytically to hydrogen. So they don't apply to helium even. But they're good approximations. We can bring them together and we can make molecular orbitals out of them, but our energies are going to be off a little bit. And so that's why we use all these approximation methods. And it gets incredibly complex, but that's why we have these computer programs. So we've come a long way from the hydrogen Hamiltonian. Okay. But the reason we have this huge alphabet soup of all of these options in computational chemistry is twofold. One, there's a bunch of different ways to approximate this. And two, there are researchers that this is what their research is about, is coming up with approximations for electron correlation. And so, your research group does this and you publish a paper and you modify the Gaussian code and then they incorporate it. And then you do the same thing and your code is incorporated into Gaussian. So Gaussian is just collecting the results of these researchers and putting it into their software to give everybody options. Okay. So it makes it for the user really confusing. What do we use? All right. It's just, there are too many options. So if you'll notice in that Forsman book on pages 8 through 13 that I was having you read, they talk about this APFD model and the basis set and so on. And so they've kind of helped guide us. They've done the work to say this is really good as a general model for most molecules. And so we'll just use these general models. But like if your research is on particular transition states of a particular type of molecule, you might find that there's a different model that's more accurate for that particular application. Yeah. And so this is how we can select a model chemistry. And this whole table is on page 8 of Forsman 3rd edition. These models must approximate the Hamiltonian. And so here's a sort of a survey of all the different models that are available. We have molecular mechanics models, semi-empirical models, ab initio models, and configuration interaction, or I think now they're called coupled cluster, and then density functional theory. And so we're going to go through each of these in a little bit more detail. So the molecular mechanics is one way to get rid of electron correlation is just to forget about the electrons. So they ignore all the electrons, and so that makes this really fast. If you think about it, if you bring a carbon atom in and you're going to deal with the electrons individually, you've got 6 electrons to keep track of. And if you're using a molecular mechanics model, you bring a carbon in and you just have one atom, one particle to deal with instead of a carbon nucleus and 6 electrons. So instead of bringing in 7 particles, you just brought in 1. And what they do is they have an enormous lookup table. And they say, okay, carbon bonds to other carbons with this average bond length. And so they'll program that in. And then you say, well, let's make it a little more sophisticated. Is it an sp3 carbon or an sp2 carbon or an sp carbon? So they'll have a different entry in that table for an sp carbon bonded to another carbon. So a acetylene, a triple bonded carbon, has a certain bond length, or a double bonded carbon, an ethene, or a single bonded carbon, an ethane. And so it'll have a lookup table and say, I've got a carbon bonded to a carbon. Let's go find the bond length for that and the bond energy for that. And we'll stick that in and we'll solve for the energy. If it's a little bit further than that bond length, then the energy's higher. If it's a little bit closer, it's higher. But if it's right at that bond length, that's the minimum. And that's the potential we're showing here, something like that. So you have the bond energy here. And it's pairwise. And so this also is the energy for each pair. So when calculating this, it will take your structure, pick atom 1, and calculate the distance to every other atom in the molecule. And it'll calculate those distances, R1, 2. And it'll compare the lookup energy for that particular pair. Now, let's say you've got a carbon here, and there's a carbon way on the other side of that molecule, okay? And it's so far away. Essentially, you get no energy for that, okay, because they're so far away. So the ones that really dominate the energy are the ones that are close, and those are going to be the single or covalently bonded pairs. But it'll still calculate all of them because it's fast. It's just saying, what's the distance? Look up the energy. What's the distance? Look up the energy. Calculate these using this real simple equation. And so it's great for large systems like proteins and polymers. And so like we had a student working for Dr. Haynes who was doing this calculation for 200,000 or 300,000 atoms. Yeah. Using graphic processing units, his GPU computer, and was just cranking through. Using a regular PC type architecture for this calculation for his system was taking, 10 or 20 hours, to do. And then they put it on the GPU system and ran it. And Dr. Haynes said, I ran the first calculation and I thought it died because it ended so quickly. But it was like 10 times speed up, or 1/10 of the time. And he thought it broke. He's like, oh, my calculation failed, and he went in and looked and it was done. And he's like, whoa, the GPU calculation is real. it is, depending on the system and the method it's using, can it farm out the calculations? And this is incredibly parallelizable, right? Because I can assign you atoms 1 through 5, calculate all the pairs, and you do atoms 6 through 10. And, so you could be different GPUs. And I'll send you a different set of atoms. You all calculate those energies, bring them together, and it's really fast. Yeah. So this is really easy to do. You could do this by hand in Excel. Okay, it'd be tedious, but you could do it. And this is how you select it. We have 3 options in Gaussian. So in that method, we pick, if you're doing ground state, fine. But on the second drop down, you pick mechanics. And so when you pick mechanics, then you pick your particular model. This UFF is called Universal Force Field. Sounds like a science fiction or something.
Yeah, it sounds super.
Yeah, and then these Dryden and Amber, those are just named after either the researcher or the research group, as an acronym. So they're just different force fields. What in the heck is a force field? Well, just this. It's the energy term you get based upon distance, right? And so like in space, the science fiction, you can't go through this wall because there's a force field there. Because as you get closer and closer to it, your energy goes up. You bump into it and you got a really high energy and it hurts and you back off, So this is, again, these atoms have a force field around them and there's an optimal distance and so on. So that's what the idea of universal force field is. And so that lookup table of all of the pairwise differences of every type of atom is called a force field. And so this one has, when it says universal, it's an attempt to get the whole periodic table and all types of atoms, sp2, sp3, sp, etc. Tetrahedral, octahedral, those kinds of things. Then we get into semi-empirical methods. And this is trying to do the full molecular Hamiltonian, but it's trying to simplify things too by just eliminating the core electrons. Remember the picture I showed with the red ball in front of target? Mm-hmm. And the hydrogen was 71 miles across, and the sodium was to Argentina in South America. Okay, that's the valence electron in Argentina. And the core electrons are much closer to the nucleus. The chemistry is happening with the valence electrons. And so why calculate the Hamiltonian for the core electrons? It's so much more expensive. And so if I put a sodium on there, I have 11 electrons I have to calculate, when really that last one is the only one that's really important for its chemistry. And so I can reduce the problem greatly by using just the valence electrons. And so that's what semi-empirical methods do. But the problem is there's a bit of shielding of the nucleus by those core electrons, right? So that last electron on sodium, the valence electron, doesn't look at sodium and see a positive 11 charge, right? It sees something much less than that. How much of that nucleus is shielded by the first 10 electrons? And that's the fiddle factor that they use for semi-empirical methods. So they have an effective core potential. So instead of sodium being charged 11 for the Hamiltonian, it's like 1.5 or 1.2 or some factor that gives it the repeatable behavior to experiment. So like if you were to make sodium hydride, what's the bond length on that? You can do that experimentally. And then you can change the core potential in your Gaussian calculation to reproduce that bond length for sodium hydride. And if you're reproducing the bond length, you're probably reproducing the electron cloud around sodium. And so this is the semi-empirical part. So they're fiddling with the core potentials to reproduce experimental data, and then they kind of have confidence that they have a good quantum model. So the empirical part is that they've changed the core potential charge on that nucleus in the Hamiltonian to match experimental data. This behaves for atoms that obey the rules. Okay. So it's great for like a sp2 carbon or sp3 carbon, but what about the carbon atoms in this molecule? So cyclopropane. Okay, so we got a C, and a C here, and an H, right? Unless this molecule is in your training set, semi-empirical is going to do very poorly on it. Because what's the hybridization of this carbon here? I'll put sp3 with a huge question mark. Why?
Because of the angle.
What are the angles in an sp3 molecule? 109.5. What is the angle in an equilateral triangle? 60. That's a big difference. Okay, so this molecule breaks the rules. It's got 4 domains, but they're not 109.5 degrees from each other. So this semi-empirical method, we can calculate this molecule, but it's breaking the rules. It's optimized for the normal types of carbon, and this is a very strained system.
It would be inaccurate then?
It'd be inaccurate, yeah. The energy may be higher, but it won't be it may be too high actually than in reality. Yeah, so it may predict that this molecule doesn't even exist. Like every time you try to do the geometry, it makes it makes some kind of maybe, what could we do with this molecule? Like a diradical or something, like it breaks one of those bonds and makes a diradical that's got a double bond distributed over 2 bonds, and it, because it may be trying to match the 109.5 angles and the right bond distances. Okay, so your model chemistry can give you the absolute wrong answer sometimes if you're not thinking about why you're choosing that model chemistry and what your system is. So if you're trying semi-empirical methods on a really strange system like this, it may not give you an accurate picture of what nature can do. Okay. Just like if you're trying to use your model kit to make this too. Right? If you try to make this molecule with your model kit, bend those things down and they snap, then your model kit, your model breaks, not the molecule. So, yeah. And so here's how you choose it. Let me erase my markings here so you can see what we're talking about. And so these are different options. I don't do a lot of semi-empirical calculations, and so I've used AM1 and PM3. Now we have PM6, so that this PM is parametric method number 6. Austin method is AM, Austin method 1, and so this INDO is intermediate neglect of differential overlap, and I mean it's just of course, and the CNDO is complete neglect of differential overlap. The differential overlap kind of goes back to Huckel theory. Remember, you're doing Huckel theory, in like Arnie's class and so yeah. So you're looking at the overlap integrals of adjacent atoms, right? But the ones further away, you ignore. And so you're doing complete neglect of the differential overlap of the atoms further away than their adjacent neighbors, nearest neighbors. Okay, and so this again speeds things up. In doing these pairwise calculations, if it's more than 2 atoms away, we just forget about it. Yeah, and that speeds things up. So if you're going to get into something that needs semi-empirical, then just read up on it. The manuals have all of the original papers for all of these methods. So that's another thing about Gaussian. It's well documented. So you can go pull the research papers where these were developed, and you can see what their models, like for semi-empirical, what was the experimental data set that they were matching? Did it contain cyclopropane? Right? So you can go in and you can find the very molecules they used to build this program up. Now we get into, I guess, more rigorous calculations, ab initio and density functional methods. So under that theory drop-down box, our method drop-down box, we had mechanics, semi-empirical, and then we have all these other options. Okay. So these more advanced calculations require you to specify the level of theory, so how you're handling the electron correlation term in your Hamiltonian, and the basis set, so how much freedom you're giving the electrons in their wave function. And so the Hartree-Fock theory, one way to do it is to say we're just going to ignore it. So our Hamiltonian only has 4 terms instead of 5. Now you might say, how can that be legit, right? My energies are going to be inaccurate, and that's true. But if you're doing products minus reactants, the products are missing that term, the reactants are missing that term, so maybe the errors are canceled out. And surprisingly, they do. They cancel out to a large degree. And we can kind of calculate for vibrational frequencies how much error that introduces. And so we could scale our frequencies by a certain factor to correct for this at the end. At least for vibrational frequencies, we can do that. These other terms like MP2, MP4, CC are here. Mahler-Plesset perturbation theory that adds higher order terms to the Hamiltonian, and it's pretty costly. It's an attempt at an analytical solution, and so then they put that into Gaussian, but it's just really slow. It's calculation intensive. And then the coupled cluster methods. These take advantage of calculating different configurations for the electron cloud. So think about the, well, I talked about oxygen being a triplet state in its ground state. We could take that triplet state oxygen and we could calculate the configuration where it was a singlet, and we could excite the electrons, and we could calculate all of the different electron configurations, exciting a single electron into all of the excited states and still calculating. What that does is it gives us a better picture for those wave functions and how they interact with excitation. We could take 2 electrons and we could put 2 electrons in all of the different excited states. We could do 3 electrons, and that's pretty much all they've implemented. But the S, D, and T, they have coupled cluster SD, which is calculating single and double excitations. And then you could put, why they have parentheses, I don't know, but then sometimes you can put a parenthesis T in there and add in the triplet excitations too. So it's just a way to refine that wave function. Again, it's very highly accurate. It's a good way to get those good wave functions, but it really cranks up the computational time. So this would, be for what you're trying to get really small molecule calculations for a reaction or a geometry or a spectroscopy result. It's probably not going to be useful for any of y'all's research because y'all deal with big molecules like Dr. Gross's molecules and Dr. Haynes's molecules. Now let's look at density functional theory. So here are all of the different calculations that we have options for density functional theory. Now, I've been using B3LYP for, more than a decade now. And Forsman's latest edition is saying that this is a good replacement for B3LYP. So they're kind of suggesting that we start using APFD as our preferred method. And they cite in the reading that I pointed out for you this dispersion term. And so they're saying that this particular calculation method has a better ability to model the flexibility of the electron cloud, and that's going to give us better reactions. It's going to give us better spectroscopy. So this is something worth taking their advice into consideration. If you want to know what all these letters are, just go to the manual. I have no idea. Yeah. So again, this is another estimate for the electron correlation. These are using a sort of the total electron density as opposed to a single electron wave function. So it's and how they model that electron density technique is where all these letters come from. Like B3OIP are the different scientists associated with that paper. So it was originally the Becky paper, using a 3-parameter functional, which is a function of this electron density, and then Li Yang Par were the co-authors. Okay, so B3OIP is what they called this method when they implemented it in Gaussian. This APFD is Austin parameterization functional with dispersion. And so that's the new method that the Forsman book favors. So if you're going through that Forsman book and you want to calculate some of the examples, this is the method that they're suggesting you use. And then this is the theory piece. We also need a basis set. So it's 2 minutes till, so we'll start here next time and talk about basis sets. That's a nice place to stop. And I'm working hard on getting the homework calculations up. So I'm going to try to get that done by the end of the day. And then this will allow us to set that deadline next Wednesday. So we'll switch to the Wednesday deadline. So you'll have from this Wednesday to next Wednesday for this homework set. Okay? All right.